So I wanted to wrap up what we started today because we really didn't get a chance to go through this problem, and it's an optimization problem. And often with optimization, our goal is to maximize or to minimize something, and optimization is a goal in many aspects of our lives. So I wanted to go through a problem with you and go through the guidelines a little bit slower than what we were able to do in class, and we'll do a warm-up tomorrow. So the problem that we were working on, we're going to go through it step by step in line with the guideline. So the given information here that we went through was, I'll grab an ink here, that the baggage is box-shaped with the sum of the length, width, and height not exceeding 64 inches. And the dimensions and the volume of a square-based box is what we're after for maximizing. So we had to identify the constraint function and the objective function. So let's go about walking through this step by step. So the first step was just to record the given information. And we did this on the board. And the given information was the box must be the sum of the length, width, and the height was not to exceed 64. So length plus width plus height was not to exceed 64. And the dimensions and the volume of a square-based box was what we were trying to maximize. So a square-based box was another piece of information given. And we're trying to maximize volume. So three key pieces of information. So the next step was, and when we did this on the board, was to lay out a constraint function. And the constraint function was given to us in terms of the statement that the baggage must be box-shaped with a length plus a width times plus a height equaling 64, and that there was a square base. So L plus W plus height has to equal 64. And then you were given that it's square-based. So that would mean that the length and the width are equal. So this constraint is just simply 2W plus H equals 64. So that's your constraint function. The objective function is the thing that we're trying to maximize or minimize. Scroll here. Pause. Okay, for some reason the scrolling's not working. So the objective function is what we're going to maximize, and that was the volume. And the volume of any box is just length times width times height. And since the length and the width are equal, this is W squared times H. The next step is that you wanted to use the constraint function. So our next step is to use the constraint function to get the objective function all in one term. So use the constraint function to get the objective function in terms of one variable. So we're going to step through these problems in a warm-up tomorrow. We're going to step through these guidelines. So we're going to use the constraint to get the objective function in terms of one variable. Okay, so we know that the constraint function 2W plus H equals 64. So all we need to do, excuse me here, is solve for one of the variables. I'm going to solve for H in this equation. So H is equal to 64 minus 2w. And then I'm going to put that into the volume function, which is w squared h. So this is w squared 64 minus 2w. And distribute in that term, and you're left with 64 w squared minus 2w cubed. So that's your objective function in terms of one variable. The next step, which we did not get to, is now we need to find an interval of interest. Right? Because think about what we were doing with with maximizing and minimizing in chapter 6.2 and also 6.3. And that was that we looked at a function over an interval to determine where the max and the min was. So we need to define the interval of interest here. And the interval of interest, well, when is h equal to 0? When that happens, w is the largest it could possibly be. Right? It's the largest that it could possibly be. And that happens when you can set the equation equal to. I'm going to pause here for a minute. So set the equation equal to 0 and solve for w. So 64 minus 2w equals 0. That's when w is the biggest, when the height is the smallest, and that's when it's 0. So let's solve for w in this equation, and you're left with 2w equals 64. So w is equal to 32. So the interval of interest for w, it can go between 0 and the biggest that it can get is 32. So that's your interval of interest. And the last step is the step that we've been working with, and that is in chapter 4.2, and that is to find the maximum value. So we're going to find the absolute max. To do that, we take the volume function, right? Oops, not x, but the volume function. Which was equal to 64 w squared minus 2w cubed. Take the derivative of that, because we're going to need to find the critical points, and the derivative is 128 w minus 6w squared. Factor out a w. Actually, you can factor out a 2w, and you're left with 64 minus 3w. So the critical points, right, you have to set each factor equal to 0 and solve. So w is equal to 0. And over here, 3w is equal to 64. So w is equal to 64 thirds. So that's one of your, there are two of your critical points. So the critical points are 0 and 64 thirds. So to find the absolute max, I need to evaluate the function at its endpoints and also its critical points. So f of 0 is one of the critical points, which happens to be an endpoint, and f of 64 thirds, and the last one is f of 32. And that's what we do to find the absolute max. We take the critical points and the endpoints and we put it back into the original function, and we find that when we evaluate this at each of these 3 points, we find the absolute max is at 64 thirds. So, conclusion to this problem is that the absolute maximum volume, so let me write the conclusion, is the absolute max volume occurs when W is equal to 64 thirds. So when W is equal to 64 thirds, and we should plug in and find what the corresponding H value is. And when we do that, we find that H is equal to, plug it back into the equation, and solve, and you get the H is equal to 64 thirds as well. Okay, so it actually is a cube, right? So the max volume occurs when W equals 64 thirds, which means the length is 64 thirds, and we just solved for the height, and that also was 64 thirds. So to maximize the volume, it has to be a cube of length 64 thirds. And that's your answer to this maximization problem.